In this video, we're going to talk about evaluating integrals with absolute value. We're going to look at a couple different ways. We'll talk briefly about integrating over other discontinuities, jump discontinuities, and removable discontinuities. And then we'll talk about some kinds of problems that may appear on the AP exam regarding the limit process. So first, integrals with absolute value. So we're going to look at the integral from -2 to 4 of the absolute value of x dx. Now, on simple ones like this, an area argument I think is going to be the most efficient. There are some that will get more complicated, as we'll see a little bit later, that could require you to do an algebraic argument, so we'll talk about that as well. So first, the area argument. If we graph the absolute value of x from -2 to 4, it looks kind of like a big check mark like we see here. It lends itself really well to an area argument because the area between the absolute value curve and the x-axis is really just two triangles. And so we can evaluate that integral by saying we're going to get 1/2 times the base and the height of that first rectangle, or first triangle rather, and then we'll add that to the base and the height of our second triangle. So the first triangle has a base and a height of 2, so that is going to be 1/2 times 2 times 2. Our second triangle has a base of 1, 2, 3, 4, and a height also of 4. And so I guess 1/2 of 2 is 1 times 2 is 2. 1/2 of 4 is 2 times 4 is 8. So that is going to get us to 10. And that's the value of that definite integral. So the integral from -2 to 4 of absolute value of x dx is just 10. Now let's consider an algebraic argument. This is a little trickier, well, a little more involved anyway. So our definition of absolute value is as a piecewise function. So when x is greater than or equal to 0, the absolute value of x does nothing to that, what's inside of it. When x is less than 0, we say that the absolute value changes it to a positive. The way it does that is by multiplying that negative number by -1 in order to make it positive. So that means our integral from -2 to 4 is going to, from -2 to 4 will be broken up into two integrals. So from -2 to 0, where our values of x are negative, then we will actually integrate -x dx. Then on the interval from 0 to 4, where our x values are positive, we will integrate x dx. And so, doing our power rule, the integral of x is going to be add 1 to the exponent and multiply by the reciprocal of the new exponent. And then we're going to evaluate that from -2 to 0. And then I'm going to give myself some space here. And we're going to do the same thing over here. We're going to get a 1/2 x squared. And this we're going to evaluate from 0 to 4. So plugging in the 0, anything squared, 0 squared is 0, times -1/2 is 0. Then when we plug in the -2, we're going to get -2 squared is +4. -1/2 times +4 is going to be a -2. So this part is +2. Notice that's corresponding to that part that in the area argument we got was to the left of 0. And then the second piece, when we plug in 4 squared is 16, 1/2 of that is 8, and plugging in 0, 0 squared is 0, 1/2 of that is still 0, and so we're going to get 8. Notice that is going to correspond to this piece that's to the right of the vertex of our absolute value. And when we add those together, the 2 plus 8 is going to also give us the 10. So let's try another one that's a little more complicated, and we can try doing it both ways. It's a little trickier on the area argument. We just have to be very careful how we graph this. So we're going to go from 0 to 4. So here are x values. Now the vertex, remember the vertex of this absolute value is going to be where it is equal to 0. And so that is going to be at 3/2. So at 3/2, that's where, when we plug in 3/2 for x, 2 times 3/2 is going to be 3 minus 3 is 0. That's where our absolute value is going to be 0. Our boundary on the left is 0. If we plug in 0 for our x, 2 times 0 is 0, minus 3 is negative 3. The absolute value of 3 is 3, so we're going to be up here at 3. So this is going to be part of our absolute value. Now our other boundary is going to be at 4. When we plug in 4, 2 times 4 is 8, minus 3 is 5. So that means our y value is going to be up at 5. And so that's going to be right about there. So now doing an area argument, we still have our two triangles. And so we can say that that first triangle is going to be 1/2 its base, and that base is going to be 3/2 times its height, and its height we said was 3, plus the second rectangle, and its base is going to be 1, 2.5. 2.5 is 5/2 times its height, which we said was 5. So that looks like we're going to get 3 times 3 is 9, 2 times 2 is 4, so we have 9/4 from that first triangle, and that's to the left of the vertex, and then 5 times 5 is 25, the 2 times 2 in the denominator is 4, that's going to be the area of that triangle to the right of the vertex. Adding those together, 25 and 9 is 34/4. We can reduce at least by 2, call that 17/2, which is fine. Or if we would rather, 2 goes in there, you can call that 8 1/2, or 8.5. So either of those is okay. There's an area argument. So let's make an algebraic argument. So we need still where this thing is going to be equal to 0, because that is where our branches are going to be in our piecewise function. So when x is greater than or equal to 3/2, then what we get inside here is going to be positive, and the absolute value will just leave it as it is. When x is less than 3/2, then that quantity inside here is going to be negative, and so the absolute value will multiply that by -1 in order to make it positive. So now our integral is going to be divided into two pieces. So we're going to go from 0 to the 3/2. That's the part where our function, our absolute value, is negative. And I'm going to just go ahead and distribute that and call it -2x plus 3 dx. Plus we're going to get the part now to the other side of 3/2. So from 3/2 to our upper limit of 4, and that's going to be just the 2x minus 3, because in this part, in this interval, our x values will give us a 2x minus 3 that's positive, and the absolute value will leave it alone. Okay, we're going to now integrate. So the integral of x is 1/2 x squared, using our power rule, times -2 is going to be a -x squared. The integral of 3 is going to be 3x. We're going to evaluate that from 0 to 3/2. I'm going to come back to that. Plus, we're going to get here 2 times our 1/2 x squared is going to be just x squared. And the integral of -3 is -3x. And we're going to evaluate that from 3/2 to 4. Okay, plugging in the 3/2, we're going to get a negative. 3/2 squared is going to be 9/4 plus 3 times 3/2 is going to be 9/2. And then we're going to get minus. When we plug in zeros, we're just going to get zeros. I'm going to leave that for now because we may get stuff from this other integral that we can combine with that. So plugging in the 4, we're going to get 4 squared is 16, minus 3 times 4 is 12, minus, plugging in 3/2 is going to be 9/4, minus 3 times 3/2 is going to be 9/2. Well, let's see what we can combine here. For sure, the 16 minus 12 here is going to be 4. We have a negative 9/4, and another negative 9/4 is going to make a negative 18/4. I'll come back to that. We have a 9/2, and another 9/2 is going to make that be 18/2. So let's see, the negative 18/4 we can reduce to negative 9/2. The 18/2 is 9. We had that other plus 4. So let's see, that's the 9 and 4 is 13. Negative 9/2 is negative 4.5. So subtracting 4 would give us 9. Another 1/2 is going to make that be 8.5. That's good news because that's the same thing we got using the area argument. Okay? I'm going to scroll up here. Now here is one that's pretty tough because this is an example. Oops, I forgot the absolute value. Let me stick it in there. Let me see if I can still erase that. So what I really want is the absolute value of x squared minus 1. Now, because this is a quadratic, we just can't do an area argument using this one. So let's look a little bit at what's happening. The green curve you see here is our parabola. That's the x squared minus 1. It's a parabola. It opens up. It's got a vertex at 0, -1. It crosses the x-axis at 1, 0, and -1, 0. What the absolute value does is it leaves the part of the curve that's above the x-axis alone, because that's where the curve, where the values are positive. It's going to take this part where the y values are negative and make it positive, so it will reflect it up above the x-axis and give us this part of the curve here. So along here, the absolute value looks just the same as the original without the absolute value, just the x squared minus 1. And in between here is where it's going to be different. So our piecewise function, our absolute value of x squared minus 1, is going to look kind of like 3 pieces here. It's going to look like just x squared minus 1 for these values of x that are less than, or we can say or equal to, -1. And it's also going to look just like x squared minus 1 when x is greater than or equal to 1 for this part over here. On the middle part, in between -1 and 1, then that's where the curve is negative. The original x squared minus 1 gives us negative values, so the absolute value will multiply that by -1. So our integral gets much more complicated. Since we're going from -2 to 2, on that interval from -2 to -1, we're looking at this part of the graph here, which is going to be just x squared minus 1 dx. Plus the next part of the integral, when we go from -1 to 1, now we're looking at this piece here, we're going to evaluate, shall we call that a negative x squared minus 1 dx? And then once we get past 1, Now we're to this region, and we're going to go 1 to our upper limit 2 of x squared minus 1 dx once more. So the integral of x squared is going to be, we're going to add 1 to the exponent, multiply by that reciprocal, and then the integral of 1 is going to be x. So we're going to evaluate that from -2 to -1. Then we're going to get the same thing on the other part, except it's going to be a negative of 1/3 x cubed minus x, evaluated from -1 to 1, and then back to 1/3 x cubed minus x, going from -2 to -1. Okay, let's see what we get here. So I'm going to change colors so we can keep track of it. So we plug -1 in for the x. -1 cubed is -1, so that's going to be a -1/3. Minus -1 is going to be a +1. Minus, now we're going to plug in the -2. -2 cubed is -8, so times 1/3 is going to be a -8/3. And then minus a -2 is going to become a +2. There's the first part. Now we're going to get minus, and now plugging in the 1, 1 cubed is 1, so we're going to get a 1/3 minus 1. It's supposed to be a parentheses. Minus the lower limit, plugging in -1. -1 cubed is -1 times 1/3 is a -1/3. Minus -1 is a +1. Okay, that was our middle integral. Then we're going to get back to a -1 cubed is, that's not right though. Nope, I didn't have the right limits there. Let me fix those, because this was the part where we were going from 1 to 2. Okay, so 2 cubed is 8, so we're going to get an 8/3 minus 2, I'm sorry, minus the 2, so that's all part of plugging in the 2 into our antiderivative, minus plugging in the 1 is going to be 1 cubed is 1 times 1/3 is 1/3, minus 1. Okay, now we got a bunch of arithmetic to do. Let's see if we can look at all of the thirds stuff. So we have a -1/3. This is going to be a +8/3. That's going to be a -1/3. That's going to be a +1/3. That's going to be a +8/3, and then a -1/3. I think I got all of the thirds. So let's see. We've got, we can let that -1/3 and that +1/3 cancel. And we've got 8 plus 8 is 16. Minus 2 looks to me like 14/3 from that part. Now let's see if we can get the whole number parts. So we've got a 1 and then minus 2. So 1 minus 2. And we're going to get a -1 minus 1 is a -2. That negative is going to make it be a +2. And then we have a -2 here, and that's going to be a +1. So I think getting all the integers, let's see, the 2 and the -2 will kill each other off, and it looks like the 1 plus 1 minus 2 is going to just be 0. So I believe our answer is going to be 14/3, or let's see, that would be 4 2/3. Either of those would work. Whew. That's a lot of work. Okay, let's scroll up here. Now, we know that any continuous function is integrable. That is, we can evaluate the integral of any continuous function. But some discontinuities we can also integrate over. It depends on the discontinuity. We spend a lot of time, a significant amount of time in BC calculus, talking about what do you do with a vertical asymptote. We're not going to talk about that here. But if we remember what the graph of absolute value of x over x looks like, Remember, if you put in a positive number, then these are going to be the same. 1 over 1, 2 over 2, 3 over 3. So this is going to be undefined at x equals 0, because 0 over 0 is undefined. But it's always going to be 1 for positive values of x. For negative values of x, the absolute value will become positive over the negative. That's always going to be a negative 1. So think, negative 2 over negative 2. Absolute value of negative 2 is just positive 2. Divided by negative 2 is negative 1. So this is the graph of our integrand function. Then we can consider an area argument. If we're going to go from negative 1 to 3, then we can see that this area is going to be 1, this area is going to be 3, and since this area is below the x-axis, that's going to get counted as a negative, so we'll get 3 minus 1, or we can say that integral is 2. So the area that we are missing underneath a single point is negligible. Since a point has no size, then there's no area underneath just that one point. So we don't have to really worry about it. Now the next one is just a variation on the one we just did. So I moved the absolute value to the denominator. That doesn't really change much. We still are going to see that we have this x minus 3 over the absolute value of x minus 3. The x minus 3 part is going to translate our graph over here to 3. So instead of having the discontinuity at 0, the discontinuity is going to be at 3. And because of this 2, these values are going to get multiplied by 2. So if it's a vertical stretch. So that means that, again, to the right of 3, if we plug in something like 4, then what we're going to get is still going to be just a positive 1, but times that 2 is going to give us a horizontal line at 2. And to the left of 3, we're going to get a horizontal line at negative 2. Then we can again use an area argument. So since we're going from 0 to 3, well, that wasn't very interesting. I'm going to change that because I can do that. I'm going to make this go to 4 because that's a more interesting question, at least. So now we can get my tick marks back in there. So there's going to be 4. So we're going to get this area that is below the x-axis is now 2 by 3. So that's a negative 6. And this area that's above the x-axis is going to be a positive 2. And so the integral will be negative 6 plus 2, which is going to make that be negative 4. Now the third one, if you notice that at 1 here, this is going to be undefined because 1 squared minus 1 is 0 over 0. But if you factor this, you can see that this is really going to act like the integral from 0 to 2 of x plus 1, except that what happens at x equals 1, where these canceled, is we're going to have a hole in the graph. So visually, what we can see is we're going to have a straight line. We're going to have y equals x plus 1, which we hopefully know as a y-intercept of 1. And by the time we get to 2, 2 plus 1 is 3. So 1, 2, 3, we're going to be right here. So this is going to look like that straight line, except that at x equals 1, we're going to have a hole in the graph. So again, for us, the area, so we can consider this as having the area in here minus the area under a single point, which is nothing. So how you do this is kind of up to you how you want to divide it geometrically. You could, if you know your formula for the area of a trapezoid, you could do that. I imagine most people would see it as a triangle plus a rectangle. So the rectangle is 2 by 1, so that would be 2, and the triangle is going to be 1/2 the base, which is 2, and the height, which is also 2, and so that's going to be 2 plus 2 would be 4, and so that integral is going to be 4, and the area we lose underneath that 1 point is nothing. Okay. All right, now we do some more complex stuff. So the College Board wants to emphasize the connection between Riemann sums and the definite integral. This was newly introduced in the 2016-2017 cycle, although I don't think there have been many problems since then. Although in the more recent stuff that we're seeing on AP Classroom, we're starting to see more examples of these kind of problems. So I would expect that you will probably see at least one multiple choice problem of the type that we're going to talk about here. But first, let's review what we have done with the limit process. Now, I think the likelihood that you have to do something like what we have done is very, very slim. I would say 0. But it will help us to understand the kind of questions that they may ask us. So remember, this is our definition of a definite integral, it's this infinite Riemann sum. And we are going to try to fight our way through this kind of notation stuff. So let's remember, if we were going to do the limit process, the integral from 1 to 3 of x squared dx, we're going to choose a right Riemann sum. They're just easier to set up that way, and that's going to be the case, I'm sure, on the AP questions also. So here's our x squared parabola, and I have drawn 3 rectangles, but I intend that to be n rectangles. I just wanted to draw them big enough that you could sort of see them. Now, as always, our delta x is going to be b minus a over n. So in our case, the b minus a is 3 minus 1, so that's going to make our delta x be 2 over n. So remember, we said that we're going to imagine finding the areas of these rectangles, these n rectangles. So the first rectangle is going to be a base times a height. I wrote that any other way, though. This is going to be the base, which is our delta x, and this represents the height, which is going to be our function evaluated 1 delta x to the right of our left endpoint, that 1. So that's why we have the 1 plus, there's 1 delta x. Then the second rectangle is going to have that same base, the delta x, and it's going to be 2 delta x's to the right of our starting point. So that's going to look like f of 1 plus 2 over n times n, and then here's our base, the 2 over n. We continue that out to the nth rectangle, which will look something like this. Now, if we write what we have here in summation notation, that would look something like the sum k going from 1 to n of f of 1 plus 2 over n times k. See how this is our counter, because there's our 1 times 2 over n, then a 2 times 2 over n, 3 times 2 over n, and so forth. And all of those have the same delta x, the same 2 over n. Now what this f of is going to look like in our case, because we said our function is x squared, is going to be, there's our 1 plus 2 over n times k squared, because it was our squared function. That's what that's going to look like. So understanding that notation is going to be something of a key for us. So we can see that in this parentheses thing here is our function. So we're going to need to, if we see that summation, be able to identify what is the f of x. We can also see in here is this part that's in, well, first let's say maybe talk about this. That delta x is going to be key because that holds in there the b minus a over n. So in particular, that numerator 2 is going to be our b minus a. That's the difference between the endpoints, the lower limit and the upper limit of our integral. And we also see a part of that there in our counter. So this result, I'm trying to think what color I want to use here. So this in here can hold a, where a is the lower limit, plus there's our b minus a over n times k. So we're going to have to kind of be like Sherlock Holmes here and deconstruct this when we're given it and try to pick out what is that a. You know, can we identify the a, the b, and the function? Okay, let's see an example. So can we take this summation and write it as a definite integral? And in fact, there are two different ways we can do this. So one way would be to see, well, we can for sure see that the b minus a over n, the b minus a is going to be that 5. So one way to show that b minus a is 5 is to make the difference, the lower limit to the upper limit is going to be 5 apart. One way to consider that is to think of that as the a. And in that case, if the lower limit is going to be 2 and the b minus a is 5, that will make the upper limit be 7. Now we can see in here our function is kind of disguised. Remember, that's the a plus whatever cubed. So that means we could say that our function is x cubed. And so this is one possible integral coming from this Riemann sum. Now there's a second way you could do this as well. So you could make this 2 not the a, not the lower limit, but make it part of the function f of x. That is, still we have the b minus a is going to be 5 apart, but we could think of our function as being 2 plus x, that's what really that is there, cubed. Then we would be starting not at 2, but rather at 0 and still be 5 apart. So that is a second possibility that would be correct for that integral. Okay, now let's go the other direction. If I can get my screen here. Whoops. Sorry about that. I get to scroll back down where we were. Okay, so now we're going to go the other direction. So now can we write this as a Riemann sum? So in this case, we can say, let me get my pen back up here. So now we can see that our b minus a is going to be 3. And so our b minus a over n is going to be 3 over n. We can now say that our function, which is at x cubed minus 2, so we can do our summation. And we can say k going from 1 to n, and we want that to be our f of 1 plus, and we've got our b over a minus n times k, there's our counter, times 3 over n. There's our base times height of our rectangles that are all being added up. So we'll take the limit as n goes to infinity there. So our function is this function right here. And so we can write that as the summation. And we can go, let's see, that's going to be 1 plus our 3 over n times k to the third, and then that's our cube part, minus 2, So there's our function, and then times our delta x, which is the 3 over n. And we'll go k going from 1 to n, and make that the limit as n goes to infinity. Kind of crazy. Okay.